A computer should not become more reliable as it grows larger. More parts usually mean more noise, more failure, more ways for a fragile system to fall apart. But in the cold chambers, where quantum chips are being tested, something quietly different is beginning to happen. Groups of unstable qubits are learning to protect one another, forming logical qubits that may finally let quantum machines remember long enough to matter. This is not just about speed. It is about endurance, error correction, and the first real step toward computers that can simulate molecules, materials, and perhaps one day, the delicate physics beneath life itself. Thank you for spending your time here and letting this story unfold with us. If this kind of calm science helps you think, rest, or drift deeper into curiosity, please like the video, subscribe, and share it with someone who enjoys quiet cosmic questions. And let us know in the comments what time it is where you are watching from, and where in the world this video has found you. Now, let the story begin. The important change in quantum computing does not begin with a machine solving every difficult problem at once. It begins more quietly, with a fragile system becoming a little less fragile when it grows larger. That sounds almost modest. But for quantum hardware, it cuts against the central problem that has held the field in place for decades. A quantum computer is not simply a faster classical computer with a stranger name. It is a machine that tries to hold information in forms that ordinary experience never quite prepares the mind to picture. A classical bit settles into a clear state, either off or on, a definite mark in a definite register. A qubit is different until it is measured. It can carry a blend of possibilities, and when many qubits become entangled, their states can no longer be fully described as separate pieces. This is the feature that gives quantum computing its promise. But it is also the reason the machines are so difficult to build. The same openness that allows a qubit to explore many possible states also leaves it exposed to the smallest disturbances. A vibration, a thermal fluctuation, a stray field, or an imperfect pulse can push the computation away from the path it was meant to follow. For years, that fragility defined the subject more than its potential did. The question was never only whether quantum computers could show surprising behavior in carefully designed tests. They could. The deeper question was whether they could preserve that behavior long enough and accurately enough for the work to matter. This is why the most important milestone now approaching is not a headline about speed in the ordinary sense. It is not merely a contest between a quantum chip and a supercomputer on some narrow task. It is the movement from isolated physical qubits, each easily disturbed, toward logical qubits that can protect information against the noise surrounding them. A logical qubit is not a single object. It is a carefully arranged group of physical qubits acting together, so that the information is spread out rather than stored in one vulnerable place. If one piece suffers an error, the larger arrangement can reveal that something has gone wrong without destroying the information it is trying to preserve. In principle, this is the bridge between the elegant mathematics of quantum computing and machines that can survive contact with reality. The difficulty has always been that adding more qubits often added more trouble. More physical qubits meant more control lines, more interactions, more places for errors to enter, and more chances for the state of the machine to unravel before the computation finished. Scaling a quantum processor could feel like building a larger net from threads that snapped as soon as they were tightened. The promise of error correction was that, beyond a certain threshold, this relationship would reverse. Add more physical qubits in the right structure, control them well enough, measure the right stabilizing patterns, and the logical unit should become more reliable, not less. That reversal is the quiet door the field has been trying to open. Recent progress, including the public attention around Google's Willow chip, matters because it points toward that reversal in a form that is no longer purely theoretical. The detail that matters is not only that a chip contains a certain number of qubits, or that it performs a benchmark faster than a conventional system. Such demonstrations can be meaningful, but they can also distract from the harder engineering truth. A quantum processor becomes useful only when it can run a sequence of operations while keeping errors under control. In that sense, the milestone is less like a sprint and more like the first stable heartbeat of a new kind of machine. It suggests that error correction is beginning to behave as hoped, that when physical qubits are arranged into a larger protected pattern, the protected pattern can outlast its parts. This does not mean that full-scale fault-tolerant quantum computers have already arrived. The distance between a promising logical qubit and a machine capable of transforming chemistry, cryptography, materials science, or biological simulation remains large. But the direction of progress changes when the machine starts to benefit from scale. Before that point, every expansion threatens to make the problem worse. After that point, expansion becomes a path, difficult but visible. The importance of this turn becomes clearer when quantum computing is compared with the way ordinary computers advanced. Classical computing improved for generations by making components smaller, faster, and more numerous. Transistors shrank. Circuits grew denser. Heat became more difficult. But the basic logic remained stable. A transistor did not usually lose its identity because a nearby atom trembled. Its state could be copied, refreshed, checked, and driven hard by electrical engineering. Quantum information allows deeper forms of computation, but it refuses many of those conveniences. It cannot simply be copied at will. It cannot be inspected directly without changing the thing being inspected. It must be protected through indirect clues, through patterns of correlation that reveal errors while leaving the encoded information intact. That makes quantum computing feel less like ordinary electronics and more like a controlled negotiation with the microscopic world. The machine cannot overpower nature in the classical way. It must persuade certain quantum features to remain coherent while the rest of the environment is kept at a distance. This is why cooling, shielding, calibration, pulse timing, materials quality, and mathematical error correction all become parts of the same story. A qubit is not useful because it is strange. It is useful only when its strangeness can be held, shaped, and read without being crushed by the act of control. The approach to a true error-corrected regime therefore changes the emotional temperature of the field. For a long time, quantum computers lived in a space between proof and promise. They could demonstrate effects that were clearly not classical. Yet their practical future remained uncertain because noise grew too quickly. The machines were remarkable, but they were also delicate. The new milestone does not remove delicacy. It shows how delicacy might be organized into durability. A logical qubit is a kind of architectural idea, a way of saying that reliability can emerge from many unreliable pieces if their failures are structured and watched in the right way. That idea has a familiar echo across science. Brains are made of cells that fail and renew. Bodies maintain order through constant correction. Ecosystems persist through shifting balances rather than perfect stillness. In quantum computing, the same broad principle appears in a colder, more engineered form. Stability is not the absence of disturbance. Stability is the ability to detect disturbance before it becomes fatal. That is the deeper meaning of the milestone now coming into view. It changes quantum computing from a search for isolated demonstrations into a search for sustained operation. It also changes what the machines may eventually be asked to do. The most natural work for quantum computers is not ordinary arithmetic done faster. Their deeper role may be to simulate parts of nature that already behave quantum mechanically: molecules, materials, superconductors, catalysts, and perhaps certain biological processes do not become quantum only when a physicist studies them. They are quantum already. Classical computers can approximate them, sometimes brilliantly, but the cost rises sharply as the number of interacting possibilities grows. The machine must represent a wave-like system using definite symbols, and the representation can become overwhelmingly large. A quantum computer offers a different route. It can use one controlled quantum system to mirror another. Instead of forcing nature into a purely classical description, it can allow a piece of engineered nature to carry the burden directly. That possibility is why error correction matters so much. A noisy quantum demonstration may reveal a principle a reliable logical system can begin to explore. Without stability, the promise remains trapped in short experiments. With stability, even partial stability, the machine begins to approach the scale at which chemistry, materials, and complex physical models become more than examples in a laboratory talk. The milestone is therefore not a final arrival, but a change in the slope of the journey. It marks the point where the problem may stop being whether quantum information can be protected at all, and becomes how far protection can be extended. That distinction is quiet, but it is enormous. A field can survive many years of uncertainty if its central obstacle remains measurable and reducible. It becomes harder when the obstacle appears to grow with every attempted solution. Error-corrected logical qubits offer a way out of that trap. They suggest that the machines may not be doomed to collapse under their own complexity. They may, with enough precision, become stronger as they become larger. That is why the present moment carries such weight. The future quantum computer is still not here in its full form. It is not yet a universal engine for every difficult problem. It is not yet the mirror of biology, the solver of all molecular puzzles, or the hidden key to consciousness. But the first credible signs of scalable correction change the question being asked. The question is no longer only whether quantum computers can perform a strange calculation under protected conditions. The question is whether they can begin to remember themselves long enough to become instruments of science. In that shift, speed becomes secondary. The deeper milestone is endurance, because only a quantum machine that can endure its own fragility can become large enough to matter. A classical supercomputer looks powerful because it concentrates an immense amount of order into a disciplined architecture. Racks of processors, memory banks, cooling systems, and high-speed connections are arranged so that instructions can move in clean steps from one definite state to the next. This design has transformed modern science, and its achievements should not be understated. It can model weather patterns, analyze telescope data, train vast artificial networks, and search through quantities of information that would have been unimaginable only a few generations ago. Yet the same architecture that makes classical computing reliable also reveals its limits when the system being studied is not clean, not linear, and not naturally divided into isolated instructions. A brain is one of the clearest examples. It is not simply a large electrical circuit waiting to be copied onto silicon. It is a living network whose activity depends on geometry, timing, chemistry, feedback, noise, and constantly changing connection strength. Its difficulty does not come only from the number of cells inside it. The deeper difficulty comes from the number of relationships those cells maintain, and from the fact that those relationships are never still. A neuron matters because of what it is connected to, how strongly it is connected, which chemical signals surround it, what recent activity has changed its thresholds, and how its firing alters the conditions for every signal that follows. Once that is understood, the problem stops looking like a large spreadsheet and begins to look like a shifting three-dimensional weather system made from living tissue. Classical machines can approximate such systems, but they must do so by breaking them into pieces. They turn continuous activity into time steps, probabilities into numbers, molecular movement into equations, and a web of mutual influence into a sequence of updates. This is not a flaw in classical computing. It is the way classical computing works. To simulate a system, it must represent the system in symbols and then calculate how those symbols change. For many problems, this approach is powerful enough. But with a brain, the amount of representation becomes almost as difficult as the thing being represented. The familiar figure of billions of neurons is already large, but it can be misleading because it suggests that neurons are the main units of the challenge. The greater burden sits in the connections between them. Each neuron can communicate with thousands of others, and the resulting synaptic network reaches into the hundreds of trillions of possible points of influence. A model that treats those connections with biological detail has to track not just whether a signal passed through a synapse, but how the synapse changed afterward, how local chemistry altered the next pulse, how ion channels opened and closed, and how timing across many cells shifted the meaning of the signal. Even a simplified model can become heavy. A detailed model becomes something else entirely. The machine is no longer merely solving a problem. It is spending most of its effort moving the description of the problem through itself. This is the hidden friction of classical simulation. The processor may be fast, but the data must still travel. Information has to move between memory and compute units, across boards, through interconnects, into caches, and back again. Every movement costs time. Every movement costs energy. The larger the network becomes, the more the machine begins to resemble a city trying to coordinate every conversation inside it at once. Roads clog, signals queue. The calculation may be mathematically possible, but the traffic becomes overwhelming. Early brain simulation efforts revealed this in a concrete way. The Blue Brain project showed that a small piece of mammalian cortex could be reconstructed with impressive biological detail, but that detail carried a severe computational weight. A narrow column of neural tissue required enormous memory and processing effort because the machine had to follow many kinds of activity at once. Later, the use of Japan's K-computer to simulate a portion of brain activity made the problem visible in another form. Even when representing only a small fraction of the human brain, the system needed many minutes to process a single second of activity. That was not real-time thought. It was a slow reconstruction, a delayed shadow of a process that biology performs continuously. More recent supercomputers have improved the situation dramatically, especially when models are simplified and tuned for efficiency. Large-scale simulations of mouse cortex have moved closer to real-time behavior. This progress matters, and it shows that better algorithms and stronger machines can carry classical neuroscience farther than older limits suggested. But it does not erase the underlying mismatch. A classical supercomputer can become better at imitation without becoming the same kind of system as the tissue it imitates. The brain does not store a complete lookup table for its own next state. It does not appear to update every synapse through a central clock. It does not separate memory from processing in the same strict way that conventional machines do. In biological tissue, memory is partly written into the changing strength of the connections themselves. Processing and storage are folded into the same material. The act of signaling alters the future meaning of the signal. This creates an efficiency that is difficult for classical hardware to reproduce, because most classical architectures keep data and calculation physically apart, even when specialized chips bring them closer together. The simulation still has to decide what to represent, what to ignore, and how often to update every variable. The brain's own architecture does not face the same translation problem. It is not representing a brain. It is being one. That distinction becomes sharper when physical systems beyond neuroscience are considered. Molecules, turbulent fluids, plasmas, climate systems, and living cells all contain interactions that do not scale gently. A small addition to the system can add many more possible relationships. When those relationships are deeply coupled, the computational burden grows faster than intuition expects. Classical machines often handle this by reducing precision, simplifying the model, averaging details, or focusing on the variables thought to matter most. Those approximations are necessary and often useful, but they have a cost. They can miss the faint interaction that later becomes decisive. They can smooth away the irregular edge where the important behavior begins. In a linear problem, a tiny rounding error may remain tiny. In a chaotic or highly interconnected system, it may grow into a different result entirely. The computer is then no longer following the system so much as following a simplified cousin of it. The difference may be acceptable for some purposes, but not for all. If the aim is to understand the fine timing of neural activity, the folding of a protein, or the quantum state of a molecule, the lost detail can become the very thing the model needed to preserve. This is where heat enters the story, not as a side issue, but as a sign of the deeper cost. Classical computation depends on moving and resetting physical states. Transistors switch, charges move, information is written, erased, copied, and corrected through devices that are never perfectly free of resistance. As the number of operations grows, so does the waste heat that must be removed. Large computing centers are therefore surrounded by the practical machinery of thermal survival. Cooling is not decorative. It is part of the computation's price. The faster and denser the machine becomes, the harder it must work to keep itself from drowning in its own exhaust. Biology presents an uncomfortable contrast. The human brain runs on a small metabolic budget while maintaining perception, memory, movement, imagination, repair, and regulation inside a warm body. It is not infinitely efficient, and it is not a magic object outside physics. It consumes energy, produces heat, and depends on blood flow and chemistry. But compared with the industrial appetite of large computing systems, its performance remains startling. The difference does not prove that the brain is a quantum computer in the strong sense. That claim remains speculative and must be handled carefully. What the difference does show is that intelligence-like processing can exist in a physical architecture very unlike the dominant machines of the modern world. It suggests that the future of computation may not come only from faster clocks or smaller components. It may come from architectures that reduce the distance between storage and action, that tolerate noise rather than merely suppressing it, and that let physical systems perform part of the work directly. Classical machines hit friction because they are being asked to simulate worlds that do not naturally unfold as step-by-step symbol processing. They can still go far, and they will remain essential, but their limits become visible wherever connection, uncertainty, and physical detail multiply faster than memory can carry them. The wall is not a single dramatic stop. It is a gradual thickening of cost, a point where more processors, more electricity, and more cooling buy smaller gains against systems whose complexity is woven into their matter. That is why the quantum milestone matters in a wider frame. It does not simply promise a faster calculator. It points toward a way of computing in which the machine's own physics may carry some of the complexity that classical architecture has to describe from the outside. Before that future can be trusted, the old friction has to be understood for what it is, not a failure of classical computing, but evidence that some parts of nature may require a machine built closer to nature's own rules. The energy clue begins with a simple contrast that refuses to become ordinary. A large computing center has to be treated almost like a climate system of its own. Electricity enters. Instructions move through silicon, and heat rises as an unavoidable byproduct of the work. The more intense the computation becomes, the more infrastructure gathers around it, cooling loops, fans, pumps, heat exchangers, backup power, and carefully managed airflow. None of this is accidental. It is the physical shadow of classical information processing. When a transistor changes state, a material event has occurred. Charge has moved. A gate has opened or closed. A definite value has been written somewhere and often erased somewhere else. Every one of those actions takes place inside matter that resists perfect obedience. Resistance produces heat, and heat becomes the atmosphere inside which the machine must survive. This is why high-performance computation does not look like pure thought, even when it performs tasks associated with intelligence. It looks like industry. It has mass, appetite, exhaust, and maintenance. The human brain offers a quieter comparison. It runs inside warm tissue, without metal heat sinks or coolant pipes, and its energy budget remains astonishingly small for what it does. It supports perception, movement, memory, language, attention, prediction, emotional regulation, and the continual management of the body. It does not do this without cost. The brain consumes a large share of the body's energy, and its activity depends on oxygen, glucose, blood flow, ion, membranes, and countless molecular repairs. Yet, when set beside the power demands of modern computation, its efficiency becomes difficult to ignore. A brain does not require a cooling tower to recognize a face, retrieve a childhood street, adjust balance while walking, and weigh several possible decisions at once. It operates through wet chemistry, not polished silicon, and the result is not a faster version of a conventional computer, but a different physical bargain. The first lesson of that bargain is that information and energy cannot be separated forever. They may be discussed as abstract things, but in the world itself, information has to live somewhere. It has to be carried by atoms, fields, voltages, molecular shapes, or quantum states. When a classical computer manipulates information, it repeatedly forces physical systems into definite arrangements. That definiteness is the source of its reliability. A bit is useful because it can be made to mean one thing and not another. But certainty has a cost when possibilities must be discarded. Landauer's principle, one of the quiet foundations of computing physics, states that erasing information has a minimum thermodynamic cost. In practical machines, the real cost is far higher because they are not ideal reversible devices. They switch at high speed, fight leakage, correct errors, move data across distance, and throw away heat as they go. The deeper point is not that classical computers are poorly made. They are extraordinary machines. The point is that their way of achieving clarity is energetically expensive when scaled to immense complexity. They define, reset, isolate, and repeat. Biology often does something less rigid. A neuron does not behave like a perfect transistor. It lives near threshold. Its future action depends on recent history. chemical context, membrane voltage, local noise, and signals arriving from many directions. It is not simply off or on in the same clean engineering sense. It gathers influence until a pulse becomes likely. Then that pulse travels and changes the conditions around it. Noise is not absent. It is everywhere. Molecules jitter. Ion channels fluctuate. Synapses vary. Signals fail, strengthen, weaken, or arrive slightly early or late. In a digital circuit, such uncertainty would look like corruption. In the brain, it is part of the operating environment. Biological systems do not always defeat noise by overpowering it. They can sometimes use noise to move more easily through a landscape of possible states. This does not mean the brain is careless. It means it has evolved in a world where warmth and fluctuation are unavoidable. And so its architecture works with probabilities rather than trying to abolish them. That distinction matters because it suggests that efficiency can arise not only from faster components, but from a different relationship with uncertainty. In a classical processor, uncertainty usually has to be suppressed until a clean value can be produced. In a nervous system, uncertainty can be held long enough to become useful. A weak signal near a threshold may be amplified by fluctuation. A population of neurons may encode a probability rather than a single answer. A decision may emerge from competition among patterns instead of from a central command issuing a binary verdict. At the level of lived behavior, this can look fluid and effortless. At the level of physics, it looks like a system avoiding some of the costs that come from forcing every intermediate possibility into a sharply defined symbol. The temptation is to jump from this efficiency to a strong claim that the brain must be performing quantum computation in the same sense as an engineered quantum processor. That leap is too large. The evidence does not justify treating consciousness as a proven quantum computer, and many claims in that direction remain disputed. Warm, wet environments are generally hostile to delicate quantum coherence, and any theory that places quantum effects at the center of neural computation must explain how such effects survive long enough, remain organized enough, and influence behavior strongly enough to matter. Caution is not a retreat from mystery. It is the condition that keeps the mystery scientific. Still, the energy contrast leaves a legitimate opening. The brain's efficiency shows that nature can process information through architectures that are not modeled well by simple digital switching. Some biological systems already demonstrate subtle physical strategies in which quantum effects, vibration, and environmental noise may contribute to efficient energy movement. Photosynthetic complexes, for example, have been studied, partly because energy seems to move through them with striking effectiveness, and researchers have examined whether quantum coherence or noise-assisted transport helps guide that flow. The lesson is not that every efficient biological process is secretly a quantum computer. The lesson is more restrained and more useful. Biology can exploit physical behavior that conventional engineering once treated mainly as interference. When quantum computers enter this story, they do not need to copy the brain in order to matter. Their importance is that they make a different kind of physical computation plausible. Instead of representing every possibility as a list of classical states, a quantum system can allow amplitudes to interfere. Instead of checking paths one after another, it can arrange a calculation so that wrong paths tend to cancel and useful paths become more likely to appear at measurement. That description is still simplified, and it should not be mistaken for magic. Quantum algorithms work only under strict conditions, and they do not make every hard problem easy. But they do point toward a form of computation where possibility itself is part of the machinery. This is the deeper connection to the energy clue. A system that can process by controlled interference, reversible evolution, and carefully protected correlations may reduce some of the waste associated with brute force classical search. It does not escape thermodynamics altogether. Real quantum computers require refrigerators, control electronics, fabrication facilities, and error correction overhead. In many present forms, they are not low-energy household devices. Their dilution refrigerators can be massive, and the supporting classical systems are substantial. The promise is not that today's quantum hardware already matches the quiet efficiency of biology. The promise is that useful quantum computation may attack certain problems without expanding the classical representation until it becomes energetically absurd. This matters for problems where nature's own state space is enormous. A molecule with many interacting electrons does not examine its possible arrangements one at a time. It exists as a physical system whose behavior is already shaped by quantum rules. A classical computer trying to simulate it may spend vast resources describing those possibilities from the outside. A quantum computer, if stable enough, could encode aspects of that behavior more directly. In the same way, certain probabilistic or highly correlated biological models may benefit from machines that are not forced to flatten every uncertainty into ordinary bits at every step. The energy clue, therefore, does not prove a single grand theory of the brain. It points to a mismatch between the way classical machines spend energy and the way nature often arrives at organized behavior. Heat marks the boundary because it reveals how much effort is being used to impose order rather than inhabit it. The brain, for all its unknowns, inhabits its physical medium with extraordinary intimacy. It stores, processes, repairs, and adapts in the same living material. Classical computers remain powerful partly because they separate and discipline those functions. Quantum computers may become powerful in selected domains because they allow controlled physical uncertainty to do some of the work that classical machines must labor to describe. The next step is not to declare that the mystery has been solved. It is to examine the obstacle that makes this new kind of computation so difficult. The same openness that gives quantum systems their depth also makes them vulnerable to the world around them. A qubit fails in a way that is almost too subtle for ordinary language. It does not break like a wire, burn like a fuse, or freeze like a corrupted memory chip. It loses the delicate relationship that made it quantum in the first place. The state remains physical, but the useful pattern of possibility has leaked into the surrounding world. A quantum computer depends on keeping a qubit in controlled superposition, and often on binding many qubits together through entanglement, so that the calculation is carried by correlations rather than by separate values marching in line. The difficulty is that the universe is always trying to listen. Any unwanted contact with the environment can become a kind of measurement. The qubit does not need a human observer to disturb it. A stray photon, a tiny vibration in the chip, a microscopic imperfection in the material, a pulse that arrives with slightly wrong timing, or a thermal fluctuation in the surrounding hardware can carry away information about the state. Once that information escapes, the computation no longer evolves as intended. This loss is called decoherence, and it is the central weakness around which modern quantum engineering has had to organize itself. Decoherence matters because a quantum calculation is not simply stored in a visible arrangement of switches. It develops through phase, amplitude, and interference. Phase describes how quantum waves line up with one another. Amplitude describes the weight of different possible outcomes. Interference allows some possibilities to reinforce while others cancel. A useful algorithm depends on these relationships staying coherent long enough for the final measurement to favor the answer being sought. If the phases drift randomly, the interference pattern washes out. The machine may still return an answer, but the answer has lost the quiet structure that gave the computation its advantage. It becomes noise wearing the shape of a result. This is why early quantum computers could appear so promising and so limited at the same time. They could show the behavior expected from quantum mechanics, but only briefly, only under careful conditions, and only before accumulated errors overtook the signal. The fragility was not a small engineering inconvenience. It was the boundary between a scientific demonstration and a useful instrument. The problem becomes harder because quantum information cannot be protected in the familiar, classical way. Ordinary computers can copy data, compare copies, and replace a damaged bit with a clean one. If a classical bit should be 1 but flips to 0, the machine can use redundancy to detect the odd value out and restore the intended state. Quantum information refuses this simple treatment. An unknown quantum state cannot be copied perfectly. A direct measurement would collapse the state being protected. The machine cannot simply look inside a qubit, check what it is, and put it back. Protection has to be indirect. Engineers must arrange groups of qubits so that certain kinds of errors leave detectable traces, while the encoded information itself remains hidden from the measurement. This is a deeply unnatural kind of maintenance compared with ordinary electronics. It is more like watching the ripples around a submerged object without touching the object itself. The surrounding pattern may reveal that something shifted, but the protected state must remain unexposed. Errors also come in more than one form. A qubit can suffer a bit flip, which resembles the classical change from 0 to 1. It can suffer a phase flip, which alters the relationship between wave-like components without necessarily changing the measured value in an obvious way. It can undergo leakage, drifting into a state outside the intended computational space. It can be affected by crosstalk, where the operation aimed at one qubit disturbs a neighbor. The control system itself can introduce mistakes through imperfect microwave pulses, unstable lasers, faulty calibration, or timing errors measured on scales far below ordinary sensation. In superconducting quantum processors, the qubits are artificial atoms made from electrical circuits cooled near absolute zero. In trapped ion systems, the qubits may be internal states of charged atoms held by electromagnetic fields. Other designs use neutral atoms, photon, spins in solid materials, or more exotic approaches still being developed. Each platform has its own strengths, but none escapes the same basic fact. A qubit is useful only while the world is prevented from learning too much about it. That prevention is extraordinarily demanding. Quantum processors are often placed inside environments that look less like computers than precision instruments for making a small region of matter behave as if the rest of the universe has become quiet. Superconducting devices sit inside dilution refrigerators, nested in layers of shielding and cooled until thermal agitation is drastically reduced. Trapped ions require extremely high vacuum, stable lasers, and fields tuned with great care. Photonic systems must preserve indistinguishable particles of light through optical paths where tiny losses matter. The supporting machinery can be large, complex, and very classical. A quantum chip may be the heart of the system, but around it stands a whole architecture of measurement electronics, control software, cryogenics, calibration routines, and error analysis. This arrangement reveals a useful paradox. The quantum computer is powerful because it can use delicate physical behavior, but it can exist only inside an enormous effort to keep that delicacy from dissolving. The closer the machine comes to useful work, the more control it demands. Noise does not merely threaten the qubits one at a time. It also threatens the structure of the computation across time. A useful algorithm may require many operations in sequence. Each operation has a small chance of being imperfect. Even if the probability of error seems low, repeated steps cause failures to accumulate. A calculation that begins with a clean state can gradually drift until the final measurement no longer reflects the intended process. This is especially serious because quantum advantage often requires many qubits acting together. Entanglement spreads information across the system, which is exactly what makes the machine powerful. But it also means that a local error can contaminate a larger pattern. The computation is not a pile of independent notes. It is more like a fragile chord. Disturb one tone at the wrong moment, and the harmony changes. For this reason, the central challenge is not merely building more qubits. It is building qubits whose errors are low enough, whose interactions are clean enough, and whose correction schemes are fast enough that the computation can proceed faster than disorder can spread. This is the threshold idea in its most practical form. Below a certain error rate, correction can win. Above it, correction only chases damage that grows faster than it can be repaired. The harshness of this condition explains why quantum computing has advanced through long periods of apparent contradiction. Public attention often focuses on qubit counts, because a larger number is easy to grasp. But an impressive number of unstable qubits can be less useful than a smaller number of cleaner ones. A processor with many poorly controlled elements may create a larger space of possible errors rather than a larger space of reliable computation. The true resource is not just quantity. It is quality arranged into structure. Coherence time matters, but so does gate fidelity. Connectivity matters, but so does isolation. Measurement speed matters, but so does the ability to measure the right information without disturbing the wrong information. Calibration matters because every qubit is slightly individual, shaped by the imperfections of the device that holds it. A quantum processor is therefore not a uniform grid of interchangeable points. It is a physical landscape, with valleys, biases, defects, and changing conditions that must be mapped again and again. The machine has to know itself before it can compute with confidence. This vulnerability can make the field seem almost unreasonable. Why build a computer from states that vanish when disturbed, from information that cannot be copied, from correlations that dissolve under noise, and from hardware that requires extreme isolation to perform operations that classical electronics handle in ordinary rooms? The answer is that the same features that make quantum systems fragile also make them uniquely expressive. A molecule does not ask for classical permission before its electrons occupy a shared quantum state. A superconductor does not become simple because a simulation finds it inconvenient. Nature already uses Hilbert spaces, entanglement, tunneling, spin, and interference. The complexity is not invented by quantum engineers. It is inherited from the world. If a machine can stabilize enough of that behavior, it may represent certain natural systems with a directness that classical symbols struggle to match. But that promise remains conditional. The qubit, under noise, is not yet a window into nature. It is a window with frost spreading across it. Error correction is the act of keeping enough of the glass clear for a pattern to remain visible. The movement toward reliable quantum computing therefore passes through a narrow gate. On one side are physical qubits, remarkable but transient, capable of holding possibility only briefly. On the other side are logical qubits, protected not by perfection, but by organized redundancy and constant correction. The noise never disappears. The machine simply learns to read around it, to detect its footprints without destroying the information it guards. That is why decoherence is not merely an obstacle to be mentioned before the real story begins. It is the real story, because every future application depends on whether fragile possibility can be made to persist in a world that never stops measuring it. Error correction in quantum computing begins with a contradiction that slowly becomes a method. The qubit must be protected. But the qubit cannot simply be inspected. Its state cannot be copied into a safe reserve, checked against the original, and restored in the ordinary way. Any direct attempt to look too closely destroys the very information being guarded. For a long time, this made the problem feel almost circular. The machine needed correction because noise was unavoidable. Yet the usual tools of correction seemed forbidden by quantum mechanics itself. The escape comes from a careful distinction between the information that defines the computation and the symptoms that reveal whether an error has occurred. A quantum error-correcting code does not ask what the encoded qubit is. It asks whether the larger pattern around it has been disturbed in a way that belongs to a known family of mistakes. The protected information remains hidden in correlations spread across many physical qubits, while measurements are made on auxiliary patterns that expose only the damage. In this sense, correction does not rescue a qubit as a single fragile object. It changes what a qubit means. The useful unit of information becomes distributed, less like a note written on one piece of paper and more like a shape held by many stones. Remove or shift one stone, and the shape may still be recognized. This is the logic behind the logical qubit, and it is the idea that has quietly moved from theory toward hardware. The most common way to picture this is through surface codes, where physical qubits are arranged in a kind of grid and repeatedly checked for changes in their collective pattern. The measurements do not reveal the encoded quantum information. They reveal whether the pattern has developed a scar. Each round of checking produces clues, and a classical decoder interprets those clues to infer where an error probably occurred. This part is important because quantum error correction is not purely quantum. It is a partnership between a fragile quantum system and a fast classical system watching its shadows. The classical machinery reads the error syndromes, meaning the indirect traces of faults, and decides what correction should be applied or tracked. If this happens quickly and accurately enough, the logical state survives longer than any of its individual parts. The machine is still noisy, but the noise is no longer allowed to accumulate in silence. It has to leave evidence, and the architecture is designed to make that evidence useful. For decades, the central hope was that this process would cross a threshold. If the physical qubits were too noisy, adding more of them would only create more places for failure. The protective structure would be overwhelmed, but if the physical error rate could be pushed low enough, and if operations and measurements were accurate enough, then adding more physical qubits to the code would reduce the logical error rate. In that regime, the larger system becomes more reliable because it contains more redundancy, more checks, and more room for the code to absorb local failures. This is the reversal that matters. Before the threshold, scale is a liability. After the threshold, scale becomes protection. The field has waited for clear evidence of this reversal, because without it, quantum computing remains trapped in small demonstrations. A chip may perform a remarkable experiment, yet still fail to offer a practical route toward large calculations if each added qubit adds more disorder than capacity. Once error correction begins to improve with size, the path changes shape. It does not become easy, but it becomes rational. Engineers can begin asking how many physical qubits are needed to make a logical qubit stable enough for a useful task. How many logical qubits are required for a larger algorithm? And how much overhead the whole machine can bear? These are severe questions, but they are engineering questions rather than impossibility proofs. That change in category is why recent demonstrations have drawn so much attention. When an error-corrected device shows that a larger encoded pattern can suppress errors better than a smaller one, it suggests that the machine is beginning to move in the right direction. This is not the same as saying that a universal fault-tolerant quantum computer has arrived. It has not. The logical error rates must continue to fall. The number of useful logical qubits must grow. Operations between logical qubits must become reliable. And the full overhead of running meaningful algorithms remains large. But a door that had long been described in mathematical terms is beginning to appear in hardware. The effect is subtle because it is not a single spectacular calculation. It is a change in reliability. It says that a quantum state can be kept alive not by isolating one perfect qubit, but by organizing many imperfect qubits into a system that notices its own injuries. That kind of progress can sound less dramatic than a claim of overwhelming speed. Yet, it is deeper. Speed without correction is a flare. Correction is memory. And memory is what allows a machine to build complexity across time. A useful quantum computer must do more than prepare a state and measure it quickly. It must maintain coherence through layers of gates, through entangling operations, through measurements, through feedback, and through the unavoidable imperfections of every physical device. In effect, it must keep a calculation alive long enough for the answer to become meaningful. The comparison to a thought is tempting, and it should be handled gently. A quantum computer is not thinking in the human sense. It has no experience, no intención, and no private inner world simply because it preserves a quantum state. But it does face a structural problem that living systems also face in a distant way: continuity through disturbance. A cell remains itself while molecules turn over. A brain maintains activity while individual signals fail, drift, or vanish. A quantum processor must preserve encoded information while its physical carriers remain imperfect. In each case, survival depends not on flawless parts, but on correction, redundancy, and organization. That is the meaning of the awakening. Error correction turns fragility from a fatal condition into a managed one. It lets the machine stop, depending on the impossible purity of its smallest components, and begin relying on the behavior of the whole. The technical burden is still enormous. Physical qubits must be fabricated with high consistency. Neighboring qubits must interact when required and remain quiet when not. Measurements must be fast enough to keep pace with errors, but gentle enough to avoid causing new ones. Classical decoders must interpret syndrome data rapidly, because the correction cannot arrive after the damage has already spread beyond recovery. The device has to be calibrated again and again, as if its own physical temperament were part of the program. Every improvement in materials, control electronics, pulse shaping, cryogenics, and software becomes part of the same effort. A logical qubit is therefore not only a mathematical abstraction, it is a whole stack of physical discipline compressed into one protected unit. This is why the current moment should be understood without exaggeration and without dismissal. Exaggeration would say that the age of perfect quantum computing has begun. Dismissal would miss the fact that a central principle is being tested in the form it always needed, not as a beautiful proof, but as a noisy machine trying to become more stable when made larger. The next stages will be demanding. Many logical qubits have to be connected. Logical gates have to be performed without destroying the protection. Error rates have to fall by orders of magnitude for some of the most ambitious applications. Algorithms that look elegant on paper must be matched to hardware that can actually run them. Yet the foundation is different once correction begins to work. The quantum computer no longer looks like a device forever trapped by the weakness of its own ingredients. It begins to look like an architecture that can absorb weakness. provided the weakness is known. Structured and watched. That is a profound shift in the story. The earlier era asked whether quantum behavior could be displayed. The new era asks whether quantum behavior can be sustained. Sustained behavior is what allows chemistry to be simulated with depth, materials to be explored with precision, and complex physical systems to be studied in ways that do not collapse after a few delicate steps. The machine still sits at the edge of error, but it no longer stands there passively. It listens to the pattern of its own failures and uses that pattern to continue. In that sense, quantum error correction does not remove noise from the universe. It teaches a computer to live beside it. The threshold is not a dramatic line drawn on a laboratory wall. It is a condition hidden inside the behavior of errors. A quantum processor can contain many physical qubits and still remain far from useful, because the number that matters is not only how many fragile elements have been placed on a chip. The deeper measure is whether those elements can be organized so that their collective state fails more slowly than any single part. This is where the logical qubit becomes the central figure. It is not an improved physical qubit in the ordinary sense, not a tiny object made cleaner by better fabrication alone. It is an encoded unit, a protected pattern distributed across many physical qubits, with extra qubits and repeated measurements watching for the signs of damage. The information is not resting in one place. It is spread into a structure that can survive local mistakes, because no single local mistake contains enough power to define the whole. That shift changes the meaning of reliability. In classical machines, reliability often means making each component behave predictably. In a fault-tolerant quantum machine, reliability also means arranging many imperfect components so their errors become visible before they become destructive. The logical qubit is therefore a threshold object, something that exists only when the system has crossed from isolated fragility into organized protection. To see why this matters, the scale of the required change has to be kept in view. A physical qubit may hold a quantum state for only a limited time, and each gate applied to it may introduce a small chance of error. Those errors do not need to be large. A long quantum computation can be ruined by very small imperfections, repeated many times. The threshold idea says that if the error rate of the physical operations is pushed below a certain level, then the protective code can suppress logical errors more effectively as the code grows. If the physical error rate remains too high, the opposite happens. Extra qubits add extra failure points, and the protective structure becomes a heavier version of the same instability. This is why the phrase "below threshold" carries such weight. It does not mean that a device is perfect. It means that the mathematics of protection has begun to work in the right direction. More structure can produce more endurance. More qubits, arranged properly, can make the encoded information safer rather than more exposed. This is the reversal that separates a noisy quantum processor from the first outline of a fault-tolerant computer. The word logical can make the achievement sound abstract, as if the protected qubit belongs mainly to theory. In reality, a logical qubit is intensely physical. It depends on qubits that are close enough to interact, but isolated enough not to contaminate one another. It depends on measurements that can extract error information without collapsing the encoded state. It depends on timing, because syndrome measurements have to be repeated while the computation continues. It depends on decoding, because the pattern of observed errors is rarely a simple confession. The machine sees scattered clues and has to infer the most likely chain of faults. A physical error might appear as a single disturbance in one round of measurement, or as a pattern stretched across space and time. The decoder has to decide whether a correction is needed, where the hidden error probably lies. and how to keep track of the changing logical frame. In this sense, the logical qubit is not merely a cluster of quantum devices. It is a living agreement between hardware, measurement, mathematics, and classical control. Remove any one of those layers, and the protection weakens. The threshold also changes how progress is judged. A processor with more physical qubits is not automatically closer to usefulness. A device with fewer qubits, but cleaner operations, may stand nearer to the long path of fault tolerance. This can be difficult outside the field, because scale is easier to announce than quality. Yet, the decrease is often the deeper sign. A useful quantum computer must eventually run circuits whose length would be impossible for today's noisy devices. That requires logical error rates far below the error rates of the individual components. It requires the encoded qubits to preserve information across many operations. And it requires logical gates to be performed without tearing holes in the protection. The first milestone is therefore not the final machine. It is the demonstration that the road is not pointing uphill forever. If a larger code produces a lower logical error rate than a smaller code, then the field has evidence that scaling can become a remedy rather than a poison. Once that is true, the question becomes how much engineering is required, not whether the basic principle can survive contact with hardware. There is a quiet strangeness in this kind of reliability. The logical qubit is more dependable precisely because its identity is less local. It cannot be pointed to as easily as a single circuit element. Its state is held in correlations, in relationships among parts, in a form of information that only exists as a whole. That makes it feel almost ghostly, but not in a mystical sense. It is ghostly because it resists being reduced to a single visible object. The machine protects information by refusing to store it in the place where a single error can reach it. A local fault may disturb part of the structure, but the encoded state remains defined by a wider pattern. This is one reason topological thinking has become so important in quantum error correction. In a surface code, for example, the relevant information is tied to global features of the code rather than to the exact state of one physical qubit. Local noise may scratch the surface, but it does not easily rewrite the whole encoded value unless enough errors connect into a dangerous chain. The battle is against correlated patterns large enough to cross the protective distance of the code. Code distance is the measure of how many physical errors are needed to produce a logical failure. Increasing that distance usually requires more physical qubits, and this creates the heavy overhead that makes fault-tolerant quantum computing so demanding. A single logical qubit may require many physical qubits, and a useful machine may require many logical qubits operating together. The overhead can seem discouraging because it shows how far current devices remain from the most ambitious applications. But the same overhead is also the price of turning quantum fragility into a resource that can be trusted. The threshold does not promise an efficient shortcut around difficulty. It promises that difficulty can be paid down systematically. Better physical qubits reduce the cost. Better codes reduce the cost. Faster decoders reduce the cost. Cleaner fabrication, lower crosstalk, improved measurement, and more stable control all reduce the cost. The milestone is important because it gives those improvements a common direction. Every reduction in physical error can translate into a disproportionate gain in logical stability once the system is below threshold. This is the reason the threshold has consequences beyond the laboratory. Quantum computers are often discussed through their possible end uses, from chemistry and materials to optimization, secure communication, and the eventual breaking of certain classical cryptographic systems. But none of those futures become serious until logical qubits can be made reliable at scale. The logical qubit is the currency in which real quantum computation will be paid. Physical qubits are the raw material, necessary but not sufficient. A chemical simulation that requires long, coherent evolution cannot depend on qubits that forget their state too quickly. A materials calculation that needs deep circuits cannot run on a device whose errors spread faster than the algorithm can finish. Even a modest, useful application needs not only quantum behavior, but durable quantum behavior. The threshold is therefore the moment when the subject begins to move from demonstration toward infrastructure. It is the point at which a processor stops being judged only by whether it can show a non-classical effect and begins to be judged by whether it can preserve a controlled quantum history. That history is the fragile thread running through a computation. If it breaks, the answer has no meaning. If it holds, even for longer than before, the machine begins to acquire a new kind of seriousness. Still, the threshold must not be mistaken for a rival. A reliable logical qubit is a beginning, not a completed revolution. Many such qubits must be connected. They must exchange information through logical operations. They must remain protected while gates are performed, while measurements are made, while errors are decoded, and while the surrounding classical system keeps pace. The transition from one protected qubit to a large fault-tolerant processor may prove slower and more expensive than optimistic forecasts suggest. But the conceptual boundary is clear. Before logical protection improves with scale, the future remains suspended between promise and collapse. After it improves, the machine has a principle of growth. It can be expanded with the expectation that enough care will make it stronger, not merely larger. That is why the logical qubit feels like a reliable ghost. It is not solid in the everyday sense, and it is not located in one vulnerable component. It is a protected pattern, a persistence of information across a noisy landscape. If quantum computers are nearing their most important milestone, it is because this ghost is beginning to hold its shape. A molecule does not wait for an equation to describe it. Its electrons are already moving within a field of possibilities, shaped by charge, spin, distance, symmetry, and the quiet rules of quantum mechanics. The difficulty for a classical computer begins there, because the molecule is not made from tiny planets circling a center in clean paths. It is a shared quantum object, with electrons that can occupy overlapping states and influence one another in ways that become harder to separate as the system grows. To predict the behavior of even a modest molecule with exactness, a classical machine has to represent a vast space of possible arrangements. Each added electron can enlarge that space sharply. Each interaction adds another layer of correlation. The computer tries to build a description from the outside, translating a quantum object into classical numbers and carrying those numbers through memory, approximation, and calculation. This can work beautifully when the system is small, or when clever shortcuts capture the dominant behavior. Modern chemistry and materials science already depend on such approximations. But the boundary appears when the details that were simplified become the details that decide the result. A catalyst may depend on the placement of electrons at a fleeting transition state. A battery material may depend on subtle collective motion inside a solid. A protein may change its behavior because a small chemical group shifts the energy landscape around it. In these cases, nature is not hiding its rules. It is simply using too many of them at once for a classical description to remain light. This is where quantum simulation becomes more than a technical phrase. It proposes that the best way to study a quantum system may be to build another quantum system that can be controlled. The machine does not merely calculate the molecule as a list of symbols. It prepares qubits in a state whose mathematical structure can mirror the structure of the molecule or material being studied. Then it lets the controlled system evolve under rules chosen to resemble the physical problem. The answer is not pulled from a table of all possibilities. It emerges from the behavior of the machine itself. In this sense, the hardware becomes part of the model. The border between computation and experiment becomes softer because the processor is no longer only manipulating abstract marks. It is acting as a small, engineered piece of nature, arranged so that its own quantum state carries the weight of another. This idea reaches back to one of the clearest insights in the history of the field. Nature is quantum, and a machine built only from classical logic may struggle to imitate it without paying an enormous cost. The insight is not that classical computers are useless. They remain essential for preparing the problem, controlling the hardware, correcting errors, interpreting results, and running the enormous structure around the quantum device. The insight is that some physical questions may be most naturally asked in a physical language closer to the system itself. A quantum computer can represent amplitudes, phases, and entanglement without first flattening them into a fully classical map. That does not make the work automatic. The molecule still has to be encoded. The algorithm still has to be designed. The measurements still have to be repeated enough times to extract reliable information. Error correction still has to keep the calculation from dissolving. But the direction is different. The machine is not describing the wave by measuring every imaginary drop. It is shaping a wave that can interfere in the right way. The first powerful applications may appear in places where uncertainty is not a side effect, but the central object. Chemistry is one of those places. A chemical reaction is often governed by an energy landscape, a terrain of possible arrangements through which atoms and electrons move. The lowest valley may represent a stable molecule. A ridge may represent a difficult transition. A shallow basin may trap a reaction in an unwanted form. Classical methods can estimate these landscapes. But the work becomes punishing when electron correlation is strong, meaning the electrons cannot be treated as mostly independent. Strongly correlated systems appear in catalysts, magnetic materials, superconductors, and many biological molecules. They are difficult because the behavior of each part depends tightly on the behavior of the rest. A quantum computer, if made reliable enough, can hold those dependencies directly in entangled states. It may allow researchers to ask how a reaction pathway changes when one bond stretches, when one metal atom changes its charge state, or when one surrounding molecule shifts the local field. Such answers would not simply accelerate old calculations. They could reveal physical routes that were previously blurred by approximation. Materials science carries the same promise on a larger scale. The modern world depends on materials whose useful behavior emerges from quantum structure semiconductors, magnets, superconductors, photovoltaic compounds, sensors, and the active parts of batteries. In many cases, the practical goal is clear, but the microscopic path is uncertain. A better battery requires ions and electrons to move efficiently without destroying the material that hosts them. A better catalyst requires a surface that binds molecules neither too weakly nor too strongly. A better superconductor requires collective behavior that remains ordered at higher temperatures than existing materials allow. These are not problems of simple assembly. They are problems of many particles negotiating a shared state. Classical computation can explore candidates, and machine learning can search for patterns. But both depend on representations that may miss rare arrangements. A quantum simulator could test the behavior of candidate structures in a way that respects their underlying physics more directly. It would not replace the laboratory. It would narrow the search, sharpen the questions, and identify where matter may be willing to perform a useful trick. Biological simulation is more delicate, because living systems are not quantum computers simply because molecules inside them obey quantum laws. Cells are warm, crowded, wet, and chemically active. Much of biology can be understood through classical chemistry, statistical mechanics, and network behavior. Yet at the molecular level, biology still rests on quantum foundations. Bonds form because electrons arrange themselves in certain ways. Enzymes lower reaction barriers through precise shapes and charge distributions. Proteins fold through energy landscapes shaped by countless weak interactions. Drug molecules bind or fail to bind because of geometry, electron density, hydration, and motion. A quantum computer may become useful here not by simulating an entire living brain or body at once, but by focusing on the hardest molecular pockets where classical approximation struggles. It might help describe an active site inside an enzyme, a metal center in a protein, or the electronic behavior of a molecule involved in disease. This is a more cautious and more realistic route than claims of immediate whole brain replication. The living scale remains immense, but the molecular details are real, and some of them may be exactly the kind of problem quantum machines were made to handle. The phrase nature as the program can be misunderstood if it sounds as though the machine is free from design. It is not. A quantum computer must be prepared with extraordinary care. The Hamiltonian of the target system, meaning the mathematical description of its energy and interactions, has to be mapped onto the operations available in the hardware. If the mapping is poor, the simulation will be poor. If the qubits are noisy, the signal will blur. If the measurement strategy is weak, the answer will remain buried in statistical uncertainty. Nature may provide the rules, but the computer must still be taught which part of nature to embody. This teaching is itself a scientific art. It requires physicists, chemists, computer scientists, and engineers to decide what can be represented faithfully, what can be approximated safely, and what must be left out until the hardware improves. The promise is powerful precisely because it is not universal. Quantum computers will not make every hard task easy. They will not replace classical computing across ordinary life. Their value lies in particular regions where the structure of the problem resembles the structure of the machine. A classical computer is general because it can encode almost anything, but that generality sometimes comes at a high cost. A quantum computer is difficult because it must preserve exotic states. Yet those same states can match the exotic behavior of matter. When the match is good, the machine gains an intimacy with the problem. It does not merely store a picture of correlations. It becomes a controlled arena in which correlations can exist. The deeper milestone of error correction therefore returns here with new importance. Without reliable logical qubits, nature, as the program, remains a short performance, interrupted by noise before the useful pattern has formed. With reliable logical qubits, the performance can lengthen. The machine can begin to follow the evolution of a system through enough steps to reveal something new. It can move from suggestive demonstrations toward calculations that chemists, physicists, and biologists can trust. The change will probably arrive gradually, through narrow successes rather than a single universal breakthrough. A molecule computed more accurately here, a material property clarified there, a reaction pathway made less mysterious. Each success would show the same thing in a different domain that a controlled quantum machine can sometimes let nature answer in its own grammar. That is the quiet power of this approach. The computer stops being only a tool for representing the world and becomes, in a limited but profound sense, a small piece of the world arranged to ask a question back. The brain enters the quantum story with unusual force because it sits at the crossing point between physical complexity and personal meaning. A molecule can be treated as a chemical problem, a material as an engineering problem, and a superconducting circuit as a problem of controlled hardware. The brain is harder to hold at that distance. It is a living organ made from cells, proteins, membranes, fluids, electrical pulses, and chemical gradients. Yet it is also the place where perception, memory, decision, and consciousness appear. That double identity makes it tempting to use the most powerful language available, and quantum mechanics is often pulled into that temptation too quickly. The careful path begins by separating what is established from what remains speculative. Established neuroscience shows that neurons communicate through electrical and chemical signals, that synapses change strength through activity, that brain regions coordinate through rhythms and networks, and that cognition depends on patterns distributed across enormous numbers of cells. None of this requires the brain to be a quantum computer in the strict sense. The known machinery of nervous tissue is already rich enough to explain a great deal of behavior. At the same time, the brain is not a simple digital machine, and classical metaphors can become misleading when they suggest that neurons are merely biological transistors waiting to be copied. The truth is more restrained and more interesting. The brain is a physical system whose computation is embedded in its own material, and that makes it difficult to simulate with machines that separate memory, processing, energy, and structure so sharply. The reference point is scale, but scale alone does not capture the difficulty. A brain contains billions of neurons, yet its functional depth comes from connections, timing, local chemistry, and feedback. Synapses do not act as fixed wires. They are adjustable sites of influence. They carry history. Their strength changes with use, with neuromodulators, with development, with sleep, with disease, and with the surrounding state of the network. A neuron firing at one moment does not mean exactly the same thing as the same neuron firing under different chemical conditions. The signal belongs to a context. This is why a detailed simulation is not simply a matter of placing enough switches in a row. It requires a way to represent living relationships that are constantly being revised. Classical models can represent many of these features, and they have become increasingly powerful. They can simulate networks of simplified neurons, reconstruct microcircuits, analyze connectomes, and help explain how patterns of activity may produce behavior. But as the model becomes more biologically faithful, the cost rises. More detail means more variables. More variables mean more interactions. More interactions mean more memory traffic, more time steps, and more approximation. The model can become so heavy that it loses the most important property of the thing being modeled, its ability to unfold in real time. Quantum computing enters this discussion not because it has already solved the brain, but because it may eventually help with certain layers of the problem that are physical, probabilistic, and deeply coupled. The safest examples are molecular rather than conscious. Proteins inside neurons fold, bend, change shape, and interact through chemical forces grounded in quantum behavior. Ion channels open and close through molecular conformations. Receptors respond to neurotransmitters because of shape, charge, and energy. Enzymes regulate the chemistry that supports signaling and repair. These are not abstract symbols. They are moving pieces of matter. If quantum computers become strong tools for simulating molecules, then neuroscience may benefit from that progress long before anyone approaches a full simulation of thought. A quantum machine might help model a receptor involved in memory, a protein implicated in neurodegeneration, or a small molecular environment that classical approximations treat only roughly. This would not mean that consciousness has been captured. It would mean that one physical layer beneath cognition has become clearer. That distinction matters. A brain simulation can improve medicine without becoming a mind. The speculative edge appears when the discussion moves from molecular detail to neural computation itself. Some theories have proposed that quantum effects inside cellular structures may contribute to brain function. Microtubules, which are structural components inside cells, have received particular attention because they are ordered protein assemblies that help maintain cell shape and transport. The more ambitious claims suggest that they might support coherent quantum processes relevant to consciousness. This remains controversial. Warm biological tissue is noisy, wet, and active, and long-lived quantum coherence is generally difficult to preserve under such conditions. Some biological systems may exploit quantum effects in limited ways, but showing that a subtle quantum effect exists is not the same as showing that it performs computation. And showing computation is not the same as explaining subjective experience. A cautious scientific account has to hold those steps apart. It cannot treat possibility as proof. It cannot let the beauty of an idea substitute for evidence. Still, caution should not flatten the subject into denial. Biology has repeatedly shown that living systems use physical principles in refined ways, sometimes at scales where older engineering assumptions looked too simple. The question is not whether the brain should be forced into a quantum narrative. The question is whether some future quantum methods may reveal details of brain function that classical tools struggle to preserve. That includes molecular simulation, but it may also include probabilistic modeling, optimization of complex networks, and the study of dynamical systems that live near the edge between order and instability. Neural activity is not random in the ordinary sense. Yet it is not rigidly predictable. A small change in timing, chemistry, or input can shift the path of activity across a network. This sensitivity gives the brain flexibility, but it also makes simulation difficult. Classical computers can model chaos, but they must discretize continuous behavior and manage rounding, sampling, and approximation. Quantum computers may not automatically solve chaotic systems, and claims that they effortlessly preserve infinite nuance would be misleading. But they may offer new mathematical and physical tools for representing certain correlated probability structures more naturally than conventional architectures can. That possibility is enough to make the connection worth studying, without turning it into a claim that the mind is already understood. The ethical dimension begins even before any true artificial consciousness is on the horizon. A detailed brain model could be used to test drugs, predict disease progression, refine brain-computer interfaces, or understand how injury changes network behavior. These goals are humane and scientifically valuable. They could reduce animal testing, shorten medical trials, and reveal why treatments help one patient while failing another. But higher fidelity models also create a question about what kind of thing is being modeled. A simulation of a protein does not suffer. A simulation of an electrical spike does not have an experience. A simplified network producing pain-related signals is still a model unless there is reason to think experience is present. Yet, as models become more integrated, more adaptive, and more closely tied to the physical organization of nervous systems, the boundary deserves attention. The danger is not that every neural simulation suddenly awakens. The danger is that progress may outrun conceptual clarity. Science could produce systems complex enough to raise moral questions before society has agreed on what evidence would count. Quantum computing sharpens this problem because a sufficiently advanced quantum simulation might not merely imitate some surface behavior of a system. It could, in limited domains, reproduce the physical dynamics more directly. That does not make sentience inevitable, but it makes easy dismissal less comfortable. Consciousness remains unresolved because the measurable activity of the brain and the felt quality of experience are not the same kind of description. A scan can show networks changing. An electrode can record spikes. A model can reproduce activity. None of these alone explains why there is something it is like for an organism to feel, see, remember, or suffer. Quantum theories of consciousness attempt to bridge this gap by appealing to entanglement, coherence, or fundamental physical collapse. But none has achieved broad confirmation. More mainstream theories, including those based on integration, global availability, attention, or recurrent processing, also remain incomplete. The honest position is that consciousness is still an open scientific and philosophical frontier. Quantum computers may help explore some parts of that frontier, especially by modeling physical complexity with greater depth. They do not remove the need for evidence, and they do not grant permission to treat mystery as an answer. The careful doorway is therefore narrow but real. Quantum computing may transform neuroscience first through the chemistry of neurons, then through better models of network dynamics, then through hybrid simulations that combine classical structure with quantum subroutines for the hardest physical pieces. Along that path, the brain should not be reduced to a mystical quantum object, nor should it be reduced to a digital circuit board. It is a living physical system whose order emerges from matter in motion. The promise of quantum tools is not that they immediately reveal the ghost in the machine. It is that they may finally give science a finer instrument for studying the machine, without pretending the ghost has already been explained. The future of quantum computing is unlikely to arrive as a sudden replacement of the machines already surrounding modern life. It will arrive first as a narrow addition to them, a strange and demanding engine placed beside familiar classical hardware. That shape is important because it corrects a common misunderstanding. A quantum computer is not well suited to every task. It is not needed to open a document, route an ordinary message, store a photograph, or perform the clean arithmetic that classical processors already handle with extraordinary reliability. Its value appears where the structure of the problem matches the structure of quantum behavior in correlated states, uncertain pathways, energy landscapes, molecular systems, and mathematical spaces too large for brute force exploration. For that reason, the most realistic near future is hybrid. Classical processors will continue to organize the world into usable instructions. They will manage memory, user input, databases, networks, error decoders, calibration systems, and the slow, careful framing of each problem. Quantum processors will act more like specialized physical instruments, called when a certain part of the calculation becomes too entangled, too probabilistic, or too quantum for ordinary methods to carry efficiently. The relationship may resemble the way graphics processors changed computing without replacing central processors. A graphics processor did not become the whole computer. It became the part that handled a particular kind of parallel workload better than the older architecture could. Quantum coprocessors may follow a similar but deeper pattern. They will not simply accelerate a familiar operation. They will perform a different kind of operation, one in which controlled physical uncertainty is the resource. The classical machine will prepare the question, translate it into an appropriate quantum form, send instructions to the quantum device, receive measurement results, and interpret them through statistical and mathematical filters. The quantum device will not stand alone like an isolated oracle. It will sit inside a loop. The classical side will choose parameters. The quantum side will produce samples or evolve states. The classical side will adjust, test, and send the next version back. This kind of repeated exchange is already central to many near-term quantum algorithms, and it is likely to remain important even as error correction improves. The hybrid future is therefore not a compromise made only because quantum computers are immature. It reflects the fact that classical and quantum machines are good at different parts of the scientific process. Classical systems are excellent at structure. They are stable, copyable, programmable, and deeply integrated into the technological world. Quantum systems are difficult, but they can inhabit certain forms of complexity directly. Put together, they form a layered instrument, with classical logic holding the frame and quantum dynamics carrying the portion of the problem that resists flattening. This arrangement also changes how large biological or physical simulations might become possible. A whole brain, for example, will not be placed onto a quantum chip in any simple sense. The static map of connections, anatomical regions, cell types, blood flow constraints, and recorded activity patterns would still require enormous classical storage and organization. The classical side would hold the scaffolding. It would track which regions communicate, which variables have to be updated, which data has arrived from experiment, and which level of detail is relevant at a given scale. The quantum side, if useful, would be assigned smaller but harder pieces, molecular interactions inside a receptor, strongly coupled biochemical pathways, optimization of network dynamics, or probabilistic models where classical sampling becomes too costly. The resulting system would not be a pure quantum brain. It would be a hybrid scientific model, part database, part simulation, part physical calculation, and part experimental feedback loop. That may sound less dramatic than a complete synthetic mind, but it is more plausible and perhaps more valuable. Science often advances not by copying the whole world at once, but by finding the layer where a new instrument gives sharper access. In medicine, the same pattern is likely. A hospital or research laboratory would not send every diagnostic question to a quantum computer. Classical artificial intelligence, imaging tools, statistical models, and conventional simulations will remain central. But a quantum coprocessor could be used when a specific molecular question becomes decisive. A drug candidate might need to be tested against a protein pocket whose electronic structure is poorly captured by approximate methods. A neurological disorder might involve a misfolded protein or a binding event where a small energy difference changes the outcome. A classical system could identify the candidate region, prepare possible configurations, and narrow the list of chemical questions. The quantum system could then estimate the hardest energy relationships with greater fidelity. The classical system would absorb those results and feed them into larger biological models. No single machine would understand the patient alone. The understanding would emerge from a chain of tools, each doing the part it can do best. This is the sober shape of transformation. It is not a glowing black box that answers every question. It is a new layer in the research stack, one that may make certain impossible searches merely difficult. Hybrid architectures also matter because error correction will be expensive. A logical qubit may require many physical qubits. A useful calculation may require many logical qubits. The supporting equipment will remain elaborate, and every operation will need careful scheduling. It would be wasteful to use such a resource for tasks that classical hardware already solves well. The future quantum computer will be precious, at least at first. It will be invoked selectively. Much as large telescopes or particle accelerators are used for questions that justify their complexity, classical computers will decide when the quantum device is needed, prepare the experiment, and help decide whether the output makes sense. This selectivity should not be seen as a weakness. It is how powerful instruments often enter science. They do not replace the laboratory. They add a new kind of measurement. They let researchers see a region of reality that was previously blurred, hidden, or too costly to explore. The important question is not whether quantum processors become ordinary in every object. It is whether they become reliable enough that researchers can trust them for the narrow places where they matter most. There is another reason hybrid systems are likely to dominate. Quantum results often arrive as probabilities, not as single obvious answers. Measuring a quantum state gives one outcome from a distribution to learn the distribution. The experiment may need to be repeated many times. The classical side then becomes essential for statistical reconstruction, error mitigation, uncertainty estimation, and comparison with known data, even in fault-tolerant machines. The output of a quantum computation will often require interpretation. This is especially true in scientific applications. A number produced by a quantum algorithm has to be tested against theory, experiment, and approximations from other methods. It has to be placed inside a wider model of the world. The quantum processor may generate the difficult piece, but it does not by itself decide what the piece means. Meaning belongs to the whole scientific workflow. This is why the most successful quantum systems may look less like separate computers and more like instruments embedded inside classical laboratories of data and control. The hybrid future also softens some of the more extravagant expectations around synthetic intelligence. If quantum hardware contributes to brain-inspired computing, it will probably do so through modules and subroutines before anything resembling a full cognitive system appears. Classical neural networks may use quantum-generated features. Brain-computer interfaces may use quantum methods for selected decoding or optimization tasks only if hardware becomes fast, stable, and accessible enough. Neuroscience models may call quantum simulations for molecular details while relying on classical dynamical models for network-scale behavior. The result would be a layered intelligence infrastructure rather than a single quantum mind. This does not make the future less profound. It makes it more cumulative. The most important technologies often become invisible by being absorbed into larger systems. A quantum processor may not announce itself to the end user. It may quietly improve a material, refine a medicine, guide a catalyst, or sharpen a model inside a larger classical pipeline. Its influence may appear not as spectacle, but as a series of better answers in places where old methods had reached their practical edge. In that sense, the hybrid model is not an interim stage to be discarded once quantum computers mature. It may be the mature form itself. Nature does not separate cleanly into classical and quantum layers, but human engineering must choose where each description is useful. Large objects can often be treated classically. Small interacting systems may demand quantum care. Biological systems move between these levels constantly. A hybrid machine mirrors that layered reality. It lets one architecture manage clarity while another handles ambiguity. It lets stable logic surround unstable possibility. The path ahead will involve larger logical qubit arrays, better decoders, improved cryogenic control, new algorithms, and closer collaboration between disciplines that once spoke separate technical languages. The milestone of error correction makes this future credible because it gives the quantum layer something it previously lacked: endurance. With endurance, a coprocessor can become a working part of a larger machine. Without it, it remains a brief experiment, bright but difficult to use. The coming age of quantum computing may therefore be defined not by the disappearance of classical machines, but by their partnership with a new physical language. Two engines will face the same difficult problems from different sides, one holding the frame, the other entering the uncertainty. and together they may reach places neither could reach alone. A medical simulation begins with a patient who is still far more complicated than the diagnosis attached to a chart. The same disease name can hide different molecular histories, different genetic risks, different immune responses, and different patterns of damage inside tissue. This is especially clear in the nervous system, where symptoms may appear only after a long invisible process has already changed the brain. By the time memory begins to fail, or movement becomes uncertain, or mood and cognition shift in ways that cannot be explained by ordinary fatigue. The underlying biology may have been unfolding for years. Medicine then has to work under pressure. It must infer what is happening inside living tissue without opening every layer, and it must test possible treatments in a world where each patient is unique and time cannot be paused. Classical computation has already become a powerful ally in that effort. It can compare genomes, analyze images, search medical records, model drug interactions, and identify patterns too faint for unaided judgment. But there are places where the deepest difficulty is not the amount of data. It is the physical behavior of molecules themselves. A drug does not heal because a database says it should. It works only if its atoms fit into the moving chemistry of the body in the right way, with the right energy, at the right moment, and without disrupting something essential nearby. That requirement turns medicine into a problem of shape, charge, motion, and probability. It is here, in the small physical spaces where disease begins to meet treatment, that quantum simulation may become one of the most useful forms of computation. The most familiar example is protein folding. A protein begins as a chain of amino acids, but it becomes useful only when it folds into a particular shape. That shape is not decorative. It determines what the protein can bind to, what reaction it can assist, how stable it is, and whether it will be recognized or cleared by the cell. In many diseases, the problem is not that a protein is absent, but that it has taken the wrong form, or that it gathers into harmful structures after folding incorrectly. Neurodegenerative disorders make this problem painfully important. In Alzheimer's disease, Parkinson's disease, Huntington's disease, and related conditions, misfolded or aggregated proteins are part of a wider chain of damage that affects neurons, synapses, inflammation, and cellular repair. The full diseases are not reducible to folding alone, but folding is one of the physical doors through which the illness enters. Predicting how a protein will behave is difficult because the molecule does not test its shapes one by one like a patient search through a catalog. It moves across an energy landscape, folding and refolding through countless weak interactions among atoms, water molecules, ions, and neighboring structures. A tiny energy difference can change which shape is favored. A small chemical modification can expose a sticky surface that should have remained hidden. A mutation can tilt the landscape toward a form that accumulates instead of dissolving. Classical computers can approximate these landscapes with impressive skill, and recent artificial intelligence methods have transformed structural prediction. Yet, structure is not the whole story. A still picture of a protein does not show every motion, every transition, every binding event, or every rare intermediate that may matter in disease. A drug has to act in this moving environment. It may stabilize a beneficial form, block a harmful interaction, help clear an aggregate, or bind to a pocket that opens only briefly. Those are physical questions, and many of them depend on quantum-level details of bonding, electron distribution, and energy. A fault-tolerant quantum computer, paired with classical models, could help estimate those details where ordinary approximation is weakest. It would not simulate an entire brain at atomic precision, That remains far beyond reach. But it might simulate a crucial molecular neighborhood with enough fidelity to make a difficult drug design problem less blind. The idea of a digital twin becomes more precise in this setting. In popular language, a digital twin can sound like a complete copy of a person, a perfect virtual patient waiting inside a machine. The near-term reality is more modest and more scientific. A useful digital twin would be a layered model, built from a person's genetic information, medical history, imaging data, lab measurements, and known biology. Most of that model would be classical. It would track organs, networks, risks, and treatment responses at scales where classical methods are appropriate. A quantum component would enter only where the physical question becomes too chemically subtle or too strongly correlated for easier methods to settle. In a neurological disease, that might mean examining how a patient's specific mutation changes the stability of a protein, how a drug candidate binds to a receptor variant, or how a metal ion shifts the behavior of an enzyme involved in cellular stress. The quantum processor would not replace the physician or the clinical trial. It would narrow the search space. It could tell researchers which compounds are less likely to work, which mechanisms deserve closer attention, and which molecular interactions carry hidden risk. This is not trial and error removed completely. It is trial and error made less wasteful. The ethical value of that reduction is not small. Developing a neurological drug can take many years, and many candidates fail late. After enormous cost and after patients have placed hope in them, part of the difficulty is that animal models often capture only fragments of human disease. A mouse can reproduce a pathway or a symptom, but it is not a small human. A cell culture can reveal molecular behavior, but it is not a living brain. Human trials are essential, but they are slow, expensive, and rightly constrained by safety. Better simulation cannot eliminate those limits, yet it can make each step better informed. A quantum-assisted model could help researchers avoid compounds with poor binding behavior before they enter biological testing. It could help identify side effects tied to molecular interactions that were missed by coarse screens. It could also support rare disease research, where patient numbers are too small for broad statistical methods to carry the full burden. In such cases, physics-based modeling may help fill part of the gap, not by inventing certainty, but by giving limited evidence a stronger physical foundation. The same approach could matter beyond neurodegeneration. Cancer treatment depends on mutations that alter proteins, signaling pathways, immune recognition, and drug resistance. Autoimmune disease involves molecular recognition gone wrong. Psychiatric medicine, though still difficult to connect cleanly to molecular causes, depends on receptors, transporters, enzymes, and neural chemistry that drugs must touch with great care. Even antibiotics and antiviral drugs face the problem of moving targets, where pathogens evolve around old treatments and new compounds must be found quickly. Quantum simulation may help in each case only where the quantum part of the problem is truly limiting. That qualification is essential. Not every medical challenge becomes a quantum challenge. Many failures in medicine arise from biology at larger scales, from delivery, toxicity, behavior, access, societal condition, and the complexity of living systems beyond molecular binding. A perfect calculation of a drug pocket does not guarantee that the drug reaches the tissue, avoids the liver's defenses, crosses the blood-brain barrier, or improves a person's life. Medicine is not chemistry alone, but chemistry is one of its foundations. And a stronger foundation can change what becomes possible above it. There is also a quiet danger in calling simulation precise too early. A model can look convincing because it is detailed, yet still be wrong because a crucial variable was missing. A quantum computer can produce a more accurate answer to a poorly framed question, and that answer may still mislead. The future of simulated medicine will depend as much on validation as on computation. Predicted molecular behavior must be compared with laboratory measurements. Digital twins must be tested against real outcomes. Algorithms must show not only that they are powerful, but that they improve decisions without hiding uncertainty behind technical authority. Patients are not collections of variables to be optimized from a distance. They are living organisms embedded in histories, environments, and values. The more powerful the simulation becomes, the more important it is to remember what it does not contain. Quantum computing may eventually give medicine a new kind of lens, one that looks into molecular possibility with greater physical honesty. It may allow researchers to test dangerous ideas first in controlled models, to discard weak candidates earlier, and to design treatments with a clearer view of the energy landscapes they must navigate. The milestone of reliable logical qubits matters because none of this can rest on a machine that forgets itself before the molecular story has unfolded. A treatment simulation needs endurance, correction, and trust. It needs the quantum processor to hold a delicate calculation long enough for biology to reveal a useful constraint. If that becomes possible, medicine will not become simple. It will become less blind in some of its hardest places. And that may be enough to change the path from guesswork toward repair. The unfinished threshold is reached when a technology stops being judged only by whether it can work and begins to be judged by what kind of world it may create if it does. Quantum computing is approaching that kind of boundary. The machines are still limited, still expensive, still dependent on extreme control and careful interpretation. But the direction of travel has changed. The central question is no longer confined to whether a handful of qubits can display behavior that classical machines cannot easily reproduce. It is becoming a question of endurance, trust, and responsibility. If error-corrected, logical qubits continue to improve, quantum processors may become stable enough to carry calculations through meaningful depths of time. They may begin to model molecules, materials, and selected biological systems with a fidelity that changes what science can ask. That is the milestone beneath the milestone. A reliable quantum computer would not merely add another faster instrument to the laboratory, it would place a controlled fragment of quantum nature inside the structure of human inquiry, allowing certain parts of the physical world to be explored through a machine that shares some of their own grammar. The power of that possibility is not loud. It is quiet, precise, and unsettling in proportion to how useful it may become. The first consequence is practical. Problems that once had to be simplified until they became manageable might be approached with more of their original structure intact. A catalyst could be examined not as a rough chemical guess, but as a detailed field of competing electronic arrangements. A material could be studied through the collective behavior that gives it unusual strength, conductivity, magnetism, or instability. A drug molecule could be tested against a protein pocket with a clearer sense of how charge and motion shape its chance of binding. In each case, the gain would not be omniscience. It would be a reduction in blur. Science often advances by changing the sharpness of a question. A telescope does not answer every mystery in the sky, but it changes which lights can be separated from darkness. A microscope does not explain life by itself, but it changes what can be seen inside living matter. A fault-tolerant quantum computer may become a similar threshold instrument. It may not replace existing methods, but it could reveal where existing methods have been smoothing over the very details that matter. The second consequence is conceptual. If quantum processors become reliable enough to simulate complex natural systems, the boundary between calculation and experiment becomes less familiar. A classical simulation is usually understood as a representation, a symbolic model running inside an artificial architecture. A quantum simulation can be closer to a physical analogy, because the machine's own states may be arranged to follow the same kinds of rules as the target system. This does not make it identical to the thing being studied, and it does not remove the need for verification, but it does change the character of the model. The answer is not only computed, it is allowed to form inside a controlled physical process. That carries a certain philosophical weight. Human beings have always built instruments that extend the senses, but a stable quantum computer would extend something more subtle, the ability to let nature model nature under human direction. The laboratory would not simply observe a system from outside. It would create a disciplined cousin of the system and listen to how it behaves. That kind of instrument demands humility, because its outputs may be powerful enough to guide decisions while still being indirect, statistical, and vulnerable to misinterpretation. The third consequence is biological, and it must be approached with patience. The dream of simulating life is older than quantum computing, and it has often been inflated by metaphors that make the brain sound easier to copy than it is. Living systems are not merely complicated objects. They are histories in motion. A cell carries chemistry, structure, repair, memory, and response in the same small volume. A brain carries the changing state of a body, a past, an environment, and a network of cells whose signals are never just signals by themselves. Quantum computing may help with pieces of this difficulty, especially at the molecular level, but it will not collapse the whole problem into a single breakthrough. The most important future may be layered rather than total. Classical systems may map the structure, store the data, and coordinate the model. Quantum systems may examine the hardest physical pieces. Experiments may correct both. Medicine may then draw from the combined result, not as a perfect oracle, but as a better guide through molecular uncertainty. That path is less dramatic than creating a complete artificial mind, but it may be the path that most directly reduces suffering. The fourth consequence is ethical. A more powerful simulator changes the distance between thought and intervention. If a new material can be tested before it is manufactured, industry can move faster. If a drug can be screened before it reaches living tissue, medicine can become safer. If a biological model becomes detailed enough to predict individual response, treatment can become more personal. These are desirable outcomes, but speed and precision also create new pressures. Decisions may begin to rely on models that few people can fully understand. Companies and governments may race to use simulated results before their limits are carefully known. Security systems may need to change if future fault-tolerant machines threaten forms of encryption that protect modern communication. Access may become uneven, with the richest institutions gaining the first benefits of a technology built from rare expertise. Expensive infrastructure, and specialized hardware. A milestone in computation is never only technical. It redistributes capability. Once capability moves, responsibility has to follow. The fifth consequence reaches back into the question of mind, where caution is most necessary. A quantum computer that simulates molecules does not become conscious. A quantum computer that models neural activity does not automatically feel. Even a detailed brain model may remain a scientific object rather than a subject of experience. Yet progress in modeling lifelike complexity will force clearer definitions. At what point does a simulation become more than a tool for prediction? What evidence would suggest that a system has an inner point of view? Which kinds of modeled pain, memory, or adaptation should trigger moral concern, even if the system was built for research? These questions should not be answered by excitement, fear, or metaphor. They require slow work across neuroscience, philosophy, physics, computer science, and ethics. The danger is not that every advanced simulation is secretly alive. The danger is that society may wait too long to develop the language needed to notice if a boundary is being approached. In that sense, the most responsible position is neither denial nor fantasy. It is preparation. The sixth consequence is about trust in knowledge itself. Quantum computers will not make uncertainty disappear. Their answers will come through algorithms, measurements, repetitions, error corrections, approximations, and interpretation. They may reveal patterns that classical machines missed, but those patterns must still be tested against the world. The authority of a quantum result will depend on the clarity of its assumptions, the quality of its hardware, the honesty of its uncertainty, and the independence of its confirmation. This matters because the word quantum already carries cultural weight beyond its technical meaning. It can be used carefully, or it can be used as a decoration for speculation. A mature quantum era will need language that resists both exaggeration and dismissal. The machines will be remarkable enough without turning them into magic. Their limits will be real enough without turning them into failure. The threshold now approaching is therefore unfinished in the deepest sense. It is not a gate that opens once and reveals a complete future. It is a long crossing, made from many smaller crossings, from physical qubits to logical qubits, from demonstrations to useful calculations, from useful calculations to trusted applications, from trusted applications to public consequences. Each stage will ask for more than technical success. It will ask whether the instruments are understood, whether their power is shared wisely, whether their uncertainty is communicated plainly, and whether the systems they help create are governed with care. The most important milestone may turn out not to be a single chip, a single benchmark, or a single announcement. It may be the moment when quantum computing becomes durable enough that its promises stop being distant and begin becoming obligations. At that point, the field will no longer be only about protecting qubits from noise. It will also be about protecting judgment from haste. The machines may learn to preserve fragile quantum states across time. Science, in response, will have to preserve something equally delicate: the patience to use that power without pretending that power alone is understanding. The threshold remains open, not because the work has failed, but because the meaning of success is still unfolding. A quantum computer that can preserve its own delicate states does more than complete a calculation. It teaches engineering to operate nearer to the grain of nature itself, where possibility is not an error to be erased, but a physical structure to be held with care. Around that structure, the older machines remain essential, steady and familiar, carrying memory, logic, language, and interpretation. Beside them, the quantum processor becomes a quieter instrument, not a replacement for thought, not a shortcut around uncertainty, but a new way of asking certain questions that matter is already prepared to answer in its own terms. Molecules still fold in darkness. Materials still hide their useful arrangements inside complex fields of interaction. Living tissue still carries more motion, repair, and history than any single model can easily contain. The coming milestone does not dissolve those mysteries. It gives them firmer edges. It suggests that some parts of nature may one day be studied with less force and more resemblance, less brute calculation and more physical sympathy. Yet the work ahead remains patient. Errors must be corrected. Claims must be tested. Models must be compared with the world that inspired them. Responsibility must grow alongside capability. Because a clearer instrument does not remove the need for careful judgment. In the end, the most important milestone may be this gradual change in relationship from forcing nature into symbols, toward building machines that can briefly share its deeper rules. The future remains unfinished, but it is no longer only distant. It is forming in protected patterns, in logical qubits, in cooling chambers, in laboratories where fragility is slowly being taught to endure, and within that endurance, science finds not a final answer, but a calmer and more exact beginning.